Okay, so thank you. On behalf of our team from the Karlsruhe University of Applied Science and the Inferix company, I would like to welcome you today. In the next 10 minutes, I'm going to talk about our paper, An Architecture to Quantify the Risk of AI Models, and I'll gladly answer any of your questions at the end. So in our paper, we propose a multi-step approach to quantify the risk of AI models. And to give you an insight of why this is important, I will start with our motivation. Second, I'd like to give you an overview of our approach, both generally and then applied to the MNIST dataset, which contains images of handwritten digits. And third, I will present to you the experiments we did, and we will the result we got from these experiments. And finally, I'm going to talk about future work opportunities and draw a conclusion. Our research was motivated by the domain of assisted living. And one thing that got increasingly popular in the last year was sensor-based activity recognition systems combined with outpatient care services. And these systems can detect if residents at home are in danger or in an unusual situation, and then they can trigger an alarm or inform nursing staff. And one thing that is very important there is to evaluate the risk associated with using AI models in these systems, which is also often mandatory in life sciences. Traditionally, an AI model is evaluated by splitting the dataset into two parts, training with one set and testing with the other set, counting the percentage of correct predictions. This can lead to big problems if the test dataset does not represent the real-world scenarios sufficiently. It is possible to have a very high test accuracy, but a low real-world success rate, possibly leading to false alarms, causing not only monetary damage to the company, but in this case, even probably putting their customers' lives at risk. So, of course not always, but often ML models are trained on datasets whose representativeness for the real world is just unknown. Classifiers are often trained with clearly distinguishable classes, or furthermore, images could be generated under laboratory conditions, or the test set is just too small. In these cases, standard evaluation methods like the accuracy do not lead to reliable estimations of risk and cost. And why is that? Well, training and test, if they don't represent the real world, and the models, they can't generalize. They just know what they have seen in the training, and often in the reality, objects are hard to recognize or positioned fuzzy between classes. And well, this just results in a very low accuracy in practice and a high risk when introducing new AI models. Applied to our domain, action recognition, activity recognition systems must, for example, distinguish closely related activities like drinking a glass of water or brushing your teeth, and especially in the absence of semantic context. And we think for good assessment of model risk and quality, exactly these situations must be represented in the training and test data set. And the risk of the model in real life is defined by exactly these difficult situations. So to get a better measurement, we developed a new approach. First, we determined images that are difficult to classify. For this, we sorted the dataset by difficulty using multiple classifiers in a majority voting approach. So we let each classifier predict labels for a set of images. And then we compare their predictions with the ground truth. And the more often an image has been misclassified, the more difficult we rate that image. And Second, we run multiple experiments using difficult and easy or just different combinations of difficulties for training and test. And also tested multiple loss functions. And then third, we evaluate both qualitatively and quantitatively the model's ability to extrapolate on previously unseen data, which should be difficult. We applied this concept to the MNIST dataset, and we used multiple convolutional neural networks for this. You can see them here on the side. And they did the voting. And then we took a look at which images were misclassified. Here are some examples. For example, the number 4 is often misclassified by number 7 or vice versa. And we created 3-dimensional plots, which are on the very left side on top. These plots show the latent space of the learned model. So we take the last layers of the neural network, cut them off, and look inside the neural network. And in this space, the objects form clusters for each class. And an ideal plot would look like this, that clusters are very compact themselves, but also well separated from other clusters. And to not only visually see it, we did some more steps, and we are using the silhouette value, which is an indicator of how well the object is positioned in the clustered space. This one is ranging between -1 and 1, and a higher value means the object is better positioned. So now I would like us to take a closer look at our experiments. And what we did is, for each combination of difficulty splits, we first calculated the silhouette for each object, for each image. And the silhouette is a simple formula, and it's, as mentioned, measuring how well the object is positioned in this clustered space. We then calculate a histogram of these silhouette values, and if a lot of these silhouette values are good or high, we get an image like on the right, and else it's more spread out like on the left. So what you can see here is a run we did where in both cases we were testing with difficult data, and on the left we were training with easy data, where the silhouette values are spread across the spectrum. And this means that the difficult test data was sometimes positioned good when it's on the right, and sometimes bad, and sometimes it was just somewhere in between. And when we're training with easy and difficult data, so we put difficult data on top, histogram has a peak on the right, and many of the difficult test samples were clustered well, which means putting the difficult data into the training set led to a better clustering. We wanted to not only see this behavior visually, but also be able to measure it. And we can calculate the entropy of the histogram for this. So when the histogram is spread wide, the entropy is high. And when it has like a few peaks, it is low. And we assume that when the entropy is low, the right peak is presumably high and the clustering is well. And we also see this in this table, like we did different runs with different loss functions and different number of epochs, and we saw that the ArcFest loss performed generally a bit better than the softmax loss, and adding the difficult data to the training set led to a lower entropy. So in the future, we would like to apply our approach to the area of action recognition to support the use cases of life science. And before we do that, we plan to replace the majority voting approach by using the silhouette coefficient to separate easy and difficult samples. And this way a lot of time could be saved as the number of required classifiers is reduced, and therefore we don't have to train that long. Independently, we might also investigate into regression problems instead of classification problems, and we want to compare the results with popular benchmarks. So to sum it all up, we proposed a framework to separate a dataset into different levels of difficulty using a majority voting approach, and evaluated the robustness of models using both visual hints and also a measurable metric using the 3D plots, the silhouette histograms, and the entropy. We then applied our theoretical approach to the MNIST dataset to prove its effectiveness. The results of the experiments were, well, as expected. The easy train dataset leads to less robust models than training with the full dataset. But more importantly than that, we showed that our proposed approach works for determining the robustness of the model. And doing these models, we also saw that using the arc phase instead of softmax loss led to a better clustering and therefore more robust models in most cases we tested. So that brings me to the end of my presentation. On this slide you can see a selection of the most relevant papers. And now thanks for your attention, and you're welcome to ask questions.